So today what we'd like to do is take stock in where we are with the course. What you'll see inside the resources folder for module 4, I re-recorded the segment about descriptive and inferential statistics from last week, Thursday. And I do want to extend my appreciation to each of you for your patience. I was presenting the session from a different location, and I don't know if you heard my family in the background, but I had a granddaughter that was going bonkers in the background, and occasionally her audio may have cut through, but never mind the session in the room itself. It was pretty distracting, and I was not uh, I was not in the top of my game as far as uh, presenting things in as organized and logical a manner. And so I don't know if you remember, but toward the end I said, hey, I'm sorry. And I did sit down the next morning and re-record this segment. So this will explain the concepts in the study guide about descriptive and inferential statistics. So that's worth watching. There is an alternate recording from a colleague at UVI, Dr. Stephen Reifenberg, works in the biology department. I don't know if any of you know him, but he has a pretty decent presentation about differential and inferential, descriptive and inferential statistics and scientific method. And what I can do is put that at the bottom of the listing here. I do have some generic video segments on random number concepts and the box and whisker plot assignment that are worth watching. But I do go into exposing the developer options in Excel or in Office apps, so you can do the macro, the intro to statistical analysis, and the macro segment. So when you're doing the macro assignment, you have that. So I just wanted to make sure that everybody was aware these resources are here. And this one in particular is, well, it's a much more organized and coherent. So for what it's worth, that's where we are. What we'd like to do today is just recap. For the module, you have 3 assignments essentially, and then 2 solutions, and then an assessment. The assessment, I'm going to turn up the assessment so that it's available. And ideally, what we'd like to do is allow you to log a first attempt. So what we're finding is that a number of students have completed the assignments, but some students have not attempted a final version on a module assessment, or they haven't completed the assessments. There are fewer of you who have attempted the solutions. So this week it's all about the solutions. If we look at our timeline, what's important to understand is that there's still ample time to complete both solutions this week. You can knock out the module 4 assignments, and if you haven't retaken the final version of assessments in previous modules, now's the week to do it. You will find that as we finish today's session and Thursday's session, we only have 1 class remaining. And then Wednesday is a study day. The following week are finals. So by this time next week, we'll be starting our last class. And so what we'd like to do is continue a review of Module 4, Concepts and Methods, and then allow some time for assistance, and then go ahead and take on the first attempt of the Module 4 assessment on Thursday. That would give people ample time to complete retakes and resubmissions before the Thanksgiving break. And then you'd be in a good place to engage the final exam during finals week. As we explained before, the final exam that'll be posted will appear in Blackboard on the day and time specified by the UVI official exam schedule. And I'll be sending notice about that soon. It does not mean that you have to engage and complete the final exam at that time. You do have the rest of finals week to resubmit or to retake module assessments. And so long as you complete the final exam no later than 11:59 p.m. on 3 December, you'll be good to go. So, but once you start the exam, you won't be able to pause it. You won't be able to go back to it sometime later. You'll have to do it in one sitting. So, any questions about what we've covered to this point? So I'm going to go ahead and queue up from our, you should see another reference, quick notes on data analysis. Actually, if we roll up here to references, you should see this resource right here. What I'd like to do is just walk through some of this and then finish up with Module 4. So one of the things that's not so obvious about descriptive statistical methods, you have the quick ability to sort from least to greatest, or from greatest to least, in alphabetical order or numerical order, using simple sorting functions. And this is just a quick but effective way to reveal patterns. So the whole point of performing data analysis, either in an Excel spreadsheet or in an Access database, is that you want to perform actions and calculations where a trend manifests, right? You want a trend to present. So you're working a set of data, and if you organize it from least to greatest on any of the given fields, then that's just a quick and dirty way of seeing if there are other patterns that jump out at you. It is one of the most common ways to identify how a data element is trending, right? So if you sort by ascending or descending order, that gives you can also go ahead and then run a chart, and sometimes graphical representations after a sort are the best way to pick up on a pattern. So even after you sort, that doesn't mean that a pattern becomes clear, but one thing that you can do is run a quick sort and then create a chart. So if you had two columns in an Excel spreadsheet, that one that had to do with zip codes and one that had to do with body mass of individuals in a given zip code, you could basically work a series of quick sorts by zip code, and then you could create what's called a pivot table. That's another method that we could explain in greater detail if there's interest, but essentially what it does is it it provides quick descriptive statistics for each of the items that match a given criteria in a column. So if you sort, you'll notice that all of the same people in the same zip codes are listed in order, and then you can basically sort from there. You can sort by zip code and then sort again by body weight from least to greatest, or you could sum the body mass and or average the body mass for a given zip code to see, which zip code area has the greatest body mass for given individuals, or the greatest average body mass. So that's just one thing that's pretty obvious. There are cases when a line graph isn't helpful. And so there are other times where you want to use other types of graphical representations. Scatter plots and histograms are a great way to identify the patterns in data output, especially when the output can't be cleanly traced as an outline, right? So if you're representing data points on a graph and they're all over the place and there's no discernible line, that's one good way to take a fresh look at the data. Now, what I'd like to do next is basically walk through how variance is calculated. And then what I'd like to do is run a little further and talk about standard deviation, okay? Any questions before we go into variance? Going once. Going twice. Can somebody unmute their mic and let me know you're still alive?
Still alive.
Still alive, okay. For descriptive statistics, and remember, descriptive has to do with very concrete, very absolute determinations. So you're performing an analysis that's largely numerical. You have this descriptive statistical quality called variance. And when you calculate variance, it helps you gauge, in a nutshell, just as the name implies, how quantities vary, right? So let's pretend that let's take a simple example. The first step you're going to do is look at the data points. And if you had random data points, and maybe they wouldn't be in order, maybe the 6 data points were 50, 10, 60, 30, and so on, right? You could still work the same process. You'd get some different results based on how they vary from step to step. But let's pretend we have a clean succession of data points and something's increasing by 10 each time, right? So first data point is 10, 20, third is 30, fourth is 40, 50, 60. Everybody with me so far?
Yes,
Yep.
sir.
So the first step is to take each of the data points and add them. And that gives you a total of 210, and then divide by 6. That gives you the average or mean of 35. So if we take 210 and divide by 6, we add all of these up, we get 210. There are 6 data points, so we divide by 6. The average value for each data point is 35. All right, that's the first step. Get the average. Second step, calculate the difference between the original values and the average. So what is variance? It's how much a given value varies with respect to the average value, right? So a specific value, how different is it from the average value? That's what we're doing when we're calculating variance. Now we do take it a step further, but so in order to do that, we're going to take the first value of 10 and we take the average of 35 and subtract 10 from it, and that gives us 25. That's the first value. Second value is 20. So I take 20 and I subtract it from 35, and that gives me 15. I take the third value, 30, and I subtract it from 35. That gives me 5. I take the fourth value, that's 40. I subtract 35 from that, it gives me 5. 50, subtract 35 from that, I get 15. And then lastly, 60 minus 35 is 25. So in each case, now I have the difference between the original, each separate value, and the average value. So I have 25, 15, 5 for the first three calculations, and then 5, 15, and 25 for the last three calculations, where I subtract the average from that. Does everybody follow where I am right now? Hello?
Can you say that one more time?
So in my second step, I'm subtracting each of the data points from the average value, and that gives me a second series of numbers, 25, 15, and 5, and then 5, 15, and 25. So now I take, that's what I do in step 2. I calculate the differences between the original values and the mean or average, right? Now we determine the average in step 1. So that's where I am in step 2. Then I square the differences between each value and the mean. And that gives me a total. And I divide by 6 again, and this gives me the actual quantity we call variance. So what happens there? My first value is 25. I square it. My second value is 15. I square it. My third value is 5. I square it. My fourth value is 5. I square it. My fifth value is 15. That's this one right here. And my last one is 25. So 25 times 25 is what? Anyone? Isn't it 625? Could be wrong.
I believe it is, if I'm not mistaken.
Yeah, 625. So I could add that to memory, right? And I'll take 15 and square it or multiply it, right? 15 times 15, that's 225. I'll add it. And then 5, I'll square it. That's 25. I can just add that. And then I take another 5 and square it. That's 25, right? I'm adding it to memory. I take 15 again and square it. That's 225. We just did that. So it's a simple example, but it helps you understand the process. And then 625 again, 25 times 25. The last value is a difference of 25 between 60 and 35. So that's 625 again. I'm going to add this. And now I'll reclaim the memory or recall the memory. I get 1,750. And if I divide by 6, that gives me this value called the variance. So variance is different from the average or mean. And understanding how something varies can be very useful, right? And essentially, depending on how you work this process, it reveals how greatly a quantity changes, I guess would be the simplest. It's another way to represent how a quantity changes. Now, when you lack data from all the subjects for a defined population, the numbers that you have to work with are called a sample. This is a really important concept, right? So there are plenty of times in a scientific exploration, in research, we don't, for one reason or another, we don't have a complete set of data. We can't measure every single individual object or item or animal or plant in a given collection. If for collecting data, there are times when we can't measure everything. And so when you have a population of subjects or values and you can't use all of them, performing statistical calculations, a given set that you do have on hand, that's referred to as a sample. So when you hear the word sample, I want you to think incomplete, okay? And what's best is often to make sure that if you can, if you're in a case where you can't take every measurement or you can't use every subject in a set, if you're sampling, what you want to do is try to randomly sample. The more random a sample is, depending on the type of analysis that's being performed, the more reliable your data is considered to be. Does everybody understand when we say sample, what that means? So if I measure all 6 data points and I have only 6 data points, is that an example of sampling? Yes or no? If I have 6 items and I measure each one, and I have measured every single item, is that considered an example where sampling is being used?
Yes.
No. No, it's not. If I use some of the quantities, then it's considered sampling. If I use every single quantity or every single measure, I'm not sampling selected items or selected measures. When you hear the term sampling, it means that you're not using every data point, you're not using every measurement, you're not using every item in a population of objects, okay, or numbers. So we sample when we don't have the ability to measure everything or use every data point. And that's important to understand. Statistically, when you're sampling, there are limitations to what you can conclude when you're working with a sample instead of an entire set and every single data point is included. Okay. So you can, even though you have, even though you take great care to randomly sample values or measurements, depending on how the sample is conducted, you can get some significantly different outcomes, right? So, any questions about variance or sampling?
No.
Now, let's pretend in the previous page that the 6 values that we were showing you, these 6 values, were actually just 6 random values that we selected from a much larger set of data, right? You can get very different answers, right? So let's say that you had hundreds of other values, and we just chose 6 out of those 100. It's important when you're presenting your results to explain that you're performing a calculation against a sample of a larger population. So what you're doing is qualifying your results. So the final division you would perform when you calculate variance would use 5 rather than 6. So that's a really important distinction. What are we saying? When you're calculating variance and you have a complete set of measures or outcomes and everything's included, then you divide by the number of values, right? At the very last part, you divide by 6 because you had 6 inputs. So you calculated the average, then you subtracted the average from each individual value. That gave you a difference. Then you squared the differences. Then you added the squares of differences. Then you divide by 6. That's what you do when you have a complete set of data or measures. But if you're dealing with a sample and you have only a partial set, so if we say, okay, I gathered 6 points, but there were hundreds of data points, then to calculate variance, you would do something a little different. And you do it differently because it's one way of accounting for the fact that you're only using part of the numbers. You're not, in layman's terms, calculating variance a little differently in that case is appropriate because you're not using every value or every measure. So if you had a much larger set of data and you only used 6 subjects, you would basically take the number of subjects that you used out of the sample, you would subtract 1 from that, and you would divide the sum of the squares of differences. That's what we call this, the sum of the squares of differences. You would divide that by 1 less than the number used for a sample in order to do that. Now you'll see a lot of formulas in math where they use n as a symbol, and then they tell you, if n equals 6, then you divide by n minus 1, right? So if using letters for any given scenario when you're calculating variance helps you understand that better, let's pretend that the number of values in a sample was 187 samples. And I know that there are thousands of measures or thousands of values, but I only have 187. And I go through step 1, step 2, and step 3. When I get to step 3, if I used a sample of 187 values to calculate a subset or a partial set of inputs, what would I divide by to get my final answer? From the sum of the squares of differences. If I had 187 out of thousands, what would I divide by? If I had 187 data points used for the calculation. If n was equal to 187, what's n minus 1?
186.
186 is correct. So I would divide the sum of the squares of differences by 186 instead of 187, because I'm dealing with a sample instead of a complete a complete set of calculations. I don't know if that, that's why this reference is called Quick Notes on Data Analysis Methods, right? This is something that throws people. They're like, oh, I know what variance is. I know how to calculate variance. And then they get a different answer from the experts. And the experts, it's considered bad form if you don't know how to do some basic things, right? So just remember when you're working something called variance to get information on how values change. If you're only using partial data, you have to divide by n-1 instead of n. Any questions about variance for a full set of values versus a partial set or sample of values? Now, why do you care about variance? Well, if you have variance properly calculated, you can easily determine the standard deviation of a set of values with your descriptive analysis, right? Your descriptive statistical analysis. All you have to do is take the variance at that point and take the square root of it. So if you've gone to the trouble of calculating 291.67 and you take the square root, now you have a value that helps us understand by how much do values deviate from the norm, right? And we were talking in our last session about the bell curve. So please do take advantage of the second recording that I put in here. So I basically blanked out the recording from class last Thursday. And in the resources session recordings folder for fall 2022, this video runs about 30 minutes, a little less than 30 minutes. But this will help provide some context and background. So we're talking about variance and standard deviation. We're talking about the bell curves. So from our study guide last week, everybody remembers this, right? We're talking about how values change and how there's so deviation is how they change, right? And if there's a regular or customary manner by which measures and quantities change, the statisticians have come to understand that there's this thing called a standard deviation, and most of the values of a sampling fall within a certain percentage. So in an ideal case where you have random values that you're measuring, 68.2% basically fall within one standard deviation of the average. This would be 2 standard deviations of the average. So if there's a certain quantity that you're measuring, you can say, well, within 2 standard deviations of the population, the following is true, or the following criteria exist. What's interesting to understand is that in nature, if you take 2 standard deviations from here to here, 95% of your values lie within those ranges. And that's where a regular pattern exists. And then if you get something that's really off or different, that's significant. That's when you start to realize, hey, there's something going on here. So I want to take this back again, assuming that I had an entire population of values here, and I was not sampling. If I were performing the standard deviation, I would take the square root of 291.67. But let's pretend instead I was performing a sample. I only had 6 values out of 36 values. And I just organized these in increasing order, but let's say they occurred in different points. Some other questions you might ask is, okay, so do I get a different answer if these 6 data points are ordered differently, right? So if I order these 6 data points differently, do my calculations result in a different value? And the short answer is, because of the associative and transitive nature of mathematical functions, the short answer is, yeah, no. But let's assume that we're dealing with a sample instead of a complete population. What is my number now for a variance if this represents a sample? Can somebody tell me? N is equal to 6. So how do I get my variance when this is not a complete set? It's a sample of values. What do I divide 1750 by? Hello? I'm sampling.
You divide it by 6 to get the variance, right?
Yes, if each of those points were a complete set of data points, and I had all the data points, but let's pretend that the 6 values I have are part of a much larger set of data points or measures. Let's pretend that I have hundreds of data points and I'm just doing a quick sample. What am I supposed to divide by to get variance now? One less than 6. So if 6 is the number of points that I have for a sample, now I divide by 5 instead of 6. So I get an answer of 350 for variance. Now, why do you care? Well, standard deviation is going to be different now. So my standard deviation for a case where I'm measuring every single quantity, my standard deviation is going to be the square root of 291.67. My standard deviation is 17. So among those 6 data points, I can relate that 95% of the standard deviation is 17.08. So this bell chart, I'm sorry, what is this number? What does this number amount to? 1708 is my standard deviation. Can everybody see here? It says 34.1.
Mm-hmm.
Okay. For the example we just calculated, it's 17 instead of the 34.1. Just in terms of quantities, and I'm talking about values. So in terms of a range of values from 10 to 60, 17.9 or 17.08 represents this standard deviation on this chart. So each one of these sections, this is one standard deviation, this is a second standard deviation, this is a third, that's 2 standard deviations lower and 2 standard deviations higher. Statistically, that helps us understand what's happening with change. If I'm doing a sample, I have to subtract 1 to get my variance. So instead of dividing by instead of dividing by 6, I'm dividing by 5. And that gives me a gives me a variance of 350, and now I take the square root. So if I take the square root, my variance is higher. It's 18.771, I guess, if you round up. It's 18.71 instead of 17.08. So when we talk about descriptive analysis, there may be a case where we explain that we're doing a sample instead of a complete study, and we're going to ask you to calculate, you know, variance and standard deviation. We want you to understand how to do that by hand. Now, what's the value in doing it by hand? Well, in Excel, when you work up a spreadsheet and you have a set of values like the kinetic energy and you have a line chart, or you have a scatter plot or histogram, and you have a graph, you can click a button and it calculates standard deviation for you. It does it for you. So the reason you want to be able to understand how those values are derived is so that you can check the work. You can make sure that's what's going on. Any questions about the differences between how you calculate standard deviation when there's a sample as opposed to a complete study? In this same reference, quick notes on data analysis methods, you'll find the bottom section is about inferential statistical methods, and it talks about a regression analysis. So that's a commonly used inferential data analysis method. So for your module assessment, I may ask, okay, I'm performing a regression analysis on a set of data that I'm given. Which type of analysis is that? Descriptive or inferential? And the answer is going to be, it's inferential, right? So when both independent and dependent variables utilize a continuous data type, that's what I'm going to use, a regression analysis. Now, where have I seen that before? Well, in my study guide, there was a cheat sheet. Does everybody remember this? So my independent variable and my dependent variable are both continuous kinds of data. So I'm going to be using a regression analysis, so I can determine the relationship or correlation, right? That's where you've seen that before. There are links here that talk about scatter plot essentials and histograms, and these are worth watching real quick. So
Hey guys. Today we're going to be talking about scatter plots.
this is worth watching. It's just quick, it's informative, it explains what scatter plots are all about. I'm not going to sit here and play this for you, but you should do that, okay? And the same is also true for histograms. So there's a second link where it explains histograms. And this isn't video driven, but basically it explains how a histogram is created. So think of it as a bar chart on steroids, right? And when you should use a histogram. And we get into things like skews, right? So when there's differences or outliers, when this is a normal, typical result, and then you get different pattern bimodal meaning there are two respective peaks and values as opposed to multimodal. Here we have three. Could say this is trimodal, right? Uniform would be within a certain range, pretty much consistent. It's no lower than this and no higher than this. So unimodal would mean there's just one peak, and if it's even rising and even falling, we'd call that symmetric. If it's slanted, that's skewed to the left as opposed to skewed to the right. It's a helpful, easy to understand reference, more so than some of the stuff in our textbook. Does everybody understand what significant figures are? Anyone?
Yes.
Not really.
Okay. Let's see if we can explain it quickly. All right, so here you have a meter stick, right? And if you notice, there are teeny tiny little hash marks. What do those represent on the meter stick? Does anybody know?
Millimeters.
Millimeters is correct. Now let's pretend that you had a meter stick that didn't have any of the very small hash marks. And you had something you had to measure the length of. And all you had were the big or the larger number, the larger lines here, right? Where you see 1, 2, 3, 4, 5 all the way, right? Those are centimeter marks. So let's say you were measuring something and this meter stick was measured in decimeters. You see the number 10 here, but if it only had decimeter lines, there'd be a very heavy bold one here and a very heavy bold one there. That would be 1 decimeter, 2 decimeters, 3 decimeters, because decimeter, if you have 2 decimeters, you have 2 times 10 centimeters. So the reason you see 20 here. Anyway, I know that's kind of a quick review, but essentially let's pretend that you had a meter stick with millimeter markings, then you had a meter stick with only centimeter markings from 1 to 20 here, and then let's pretend that you had a meter stick that only had a large bold line here with the number 1 and a large bold line here with the number 2. And let's say you had to measure the length of a small lizard, and the head was here and the tail was here, right? If you were using the first meter stick, because you have the very smallest lines, you could significantly measure, right? So think of significant numbers, right? Significant means that the tool that you're using to measure is precise enough and accurate enough where you can get a good measure on it. But let's say that you had the second meter stick instead, and let's say that the tail fell somewhere between 3 and 4. Well, you'd have to guess if it was close enough to 4 or close enough to 3. And you'd write it as, 13 or 14. The point I'm trying to make is that the 3, if you don't have the tiny markings, you can't use a point so-and-so or a decimal number. That's what significant figures is all about. It all depends on the kind of measure you have to work with. Significant measures in calculations means that when you're calculating with a very rough tool of measure, your calculations are only as good as the crudest measure you have to work with. So there are people who take calculations like 2.3 and then they take pi out to 57 decimals, and then they give an answer that has 57 decimals in the answer. And the truth is, what they measured with is so crude, they can really only take it out to the first whole number. What we'd say then is that the significant figures, you draw a line over that whole number. That's how you indicate a significant figure. Probably a good idea when we talk about scientific measures. This is something they probably should have covered. Don't they cover this in Science 100? Or not?
I believe so.
They do.
Yeah. And then do they cover something?
Yeah, they do.
They cover something called absolute and relative error. Absolute error as opposed to relative error.
Something like
I don't
that, I
think
believe.
I get we covered that.
Like percentage error, I believe that's what they cover, that percentage error.
Yeah, percentage error is relative error. Excellent. Yeah. Okay. Well, that's important. It's important to understand. Sometimes when we do statistical analysis, if we're not minding the fact that some of our measures are really crude, we're passing off our statistics like it's really accurate and really precise, and it's not, because our tools of measurement are crude. Over time, we get better and better at measuring quantities, but that's part of the limitation of statistics, is that your numbers are only as reliable as what goes into them. So that's something that's good to remember. One reason that graphical analysis of a quantity is so useful is because even when there's limitations to our measuring capabilities, we can still pick up on patterns pretty quickly. And that's really the whole point of what we're doing here. So I hope you get a chance to follow down through here and read the example they provide. I just thought this was a very quick and easy example to follow. And yeah, so it talks about significant figures. I don't make mention of significant figures specifically in the study guide, but we're kind of assuming that you know something about that already because you've had Science 100 by this point. Right, so that's the end of the quick notes on descriptive and inferential data analysis, but you are going to see some items on the module assessment about these two types of measures: scatter plots, histograms, and then whisker plots, which is why you want to go back to the videos and then watch this thing about whisker plots, right? Any questions before we go on to modeling? So we were talking about samples and how you don't have the opportunity to measure everything. In a natural environment, you can't measure every turtle. You have a population of turtles and you might be able to get, you have a population of 600 turtles in a bay, and you can only measure 10 of them, right? So what you do with those numbers, it helps your analysis in terms of your integrity and credibility if you account for those differences. If you say, well, I have 6 turtles in a bay and that's the entire population and I measured all of them, and so my answers are definitive because I have the complete population measured. That makes a difference in terms of what you can conclude from the patterns, as opposed to how much confidence you have from statistical analysis when you're only working with a sample. That said, there are times where we want to generate what if scenarios. So you want to change a quantity, and you don't always have a chance to actually draw random or measure random samples. So one thing you can do is generate random numbers to use as inputs. So if you understand a relationship, if you have a formula to work with and you have some measures and one of the quantities is unknown, you can create artificial sets of data, and you can vary those so that the inputs for that are completely random, or you could increase it in a predictable manner, and in that way you could see, well, what if the body mass of a turtle increases by 10 kilograms? Can the same shark bite through the shell? I'm just using that as a quick example. So let's pretend that you're studying the survivability of sea turtles when they're attacked by tiger sharks, large sharks, right? And tiger sharks in particular. And so you understand there's so much damage to a turtle shell based on a range of sizes that you've collected from the ocean. And you know that if there's enough shell integrity that a turtle will survive. So what you can do is kind of extrapolate or calculate. When you don't know, you can simulate the experimental inputs to get a hypothetical case. What if turtles are 20 pounds? They have 10 more kilograms of mass, body mass. Now that's just an oversimplification of an example, but when you take data in computers, there are patterns that you can pick up patterns and analyze them with some code. And that type of analysis is often referred to as machine learning. So you can use code to allow a computer, to self-analyze. I want you to think of machine learning as self-analysis. So there's an algorithm or a set of calculations that can be performed, and the computer basically loops in its own inputs. That's the basis of machine learning. You might have heard of this. Artificial intelligence is a little more complex. So there are natural patterns in nature, and some are based on a mathematical concept known as fractals. Have you ever heard of fractals? Anybody here? Fractals? Fractal?
Yes. Yep.
So if you have, so in nature, there's a lot of repeating patterns that are predictable, and mathematically speaking, there's a whole class of these predictable progressions, and they can be graphically represented. They're called fractals, right? And there's just a very specific symmetry to how fractal patterns evolve in nature. Why do you care? Not too long ago, there was a discovery that there's noise in electrical lines, and the noise has a pattern to if you analyze the noise in electrical lines, there's a basic, it's fractals. To simplify things, the basis for the noise in electrical lines under certain conditions reflects fractal qualities. You can use those patterns of noise to encode digital information. So you can actually carry ones and zeros on electrical noise. Has anybody ever heard of a wireline adapter
Yes.
or a power line adapter, right? Wireline, power line adapter. You can actually put data across very large electrical, like big transformer lines. In that case, it's called power over mains. So the noise in the electric outlet can be used to embed ones and zeros, and there's a pattern, right? And the point I'm trying to make is that the basis for artificial intelligence is much richer and broader than machine learning. So on its most basic level, if you have a computer that is logging data, and then there are algorithms and instructions, successive instructions, where that data is fed in so that the machine can calculate results, and then there's a few more statements that tell the machine to, I don't know, adjust the fan speed, right? So you could write an algorithm that had machine learning built into it, where if under certain conditions, if output criteria met a certain threshold, it would mean that the fan and the fan in the computer would blow faster, right? That's just a quick example. So machine learning is a type of iterative loop where successive calculations occur automatically with a desired result in mind, right? So we're gonna create a series of feedback loops where we can run up or run down the fan speeds of computer systems so they don't overheat, right? When it gets to artificial intelligence, there's an awful lot of floating point calculations. And in order to accommodate floating point calculations, matrix computing, where you team computers together, and something called OpenGL programs with CUDA cores, you need a lot of muscle. And so one of the things that I find really fascinating about matrix computing is that it's been around a long time. Has anyone ever heard of SETI?
Think so.
I don't believe I have.
The search for extraterrestrial intelligence. Search for extraterrestrial intelligence, SETI.
Oh, you mean the guys who find aliens?
Yeah, the aliens, right? Area 51, all that kind of stuff. So SETI has been around a long time. Okay, SETI has been around since, and yeah, some folks in NASA started it. It's a fascinating organization. Used to be, you could participate in research by downloading some software. And the software, you would use the software would run, and it would run on your system when your CPU was idle. Now, what you're seeing here is Task Manager off of the taskbar. And if you're not familiar with Task Manager, you can get quick statistics on what your PC is doing. So at any given time, your computer has surplus CPU cycles it's not using, and surplus memory it's not using. So, and there's actually surplus bandwidth data flowing back and forth on the network or in Wi-Fi. Right now, in my case, I'm taking up a lot of this because we're recording, capturing all this. But to make a long story short, you have a lot of extra CPU and memory and disk capacity. The SETI program essentially made use of your extra resources to work in collaboration with hundreds and thousands and tens of thousands of other computers running the same software. So they would take noise from radio telescopes and other instruments out in space, and they would basically analyze them using hundreds or thousands of systems. Beowulf clusters is another method of doing this. So if you take a series of machines and then bind them together into a working group called a cluster, you can take a computing task and split it between all the different machines. And the name of that method, a common name for the open source method, is Beowulf. How many of you are network gamers? Do we have any network gamers in the audience?
I do.
You mean like PC lords?
Yes.
Ugh, no.
Yeah.
Well, I used to. We had-
So if you have a gaming card, a gaming graphics card,
Oh, GTX 9000s.
yeah,
Oh, those look cool.
yeah, yeah, they are. And what's interesting or most fascinating about these graphics cards is that the processor for the graphics card is very specifically designed to be very good at floating point calculations. Now, those are the same types of calculations that are used to calculate a lot of AI and artificial intelligence stuff. So what are we saying? If you get gaming graphics cards and you put them in the same computer, you can team them together. So here's a picture of a server, and you can plug those cards in and then team them together. So they're all working together. And between the multiples of graphics cards, you have the same computing power. There we go. There's an NVIDIA graphics card, NVIDIA graphics card, NVIDIA graphics card, and they're connected together with an interface called SLI. Each of those processors has hundreds of cores. So the processors have hundreds, not just dual core or 4-core or 8-core like Intel, hundreds, right? Each of them, you stitch them together, now you have thousands of those computation cores, and they're ideally suited for the same kind of calculations you use with supercomputers. You can do mathematical modeling, right? So you can basically take huge data sets, and then you can model those data sets against other overlays, like, I don't know, GPS data on maps, right? So that's the cool part. If you ever wondered, okay, how do they calculate where they think a hurricane's going? They have different models, and they use these graphics cards. They use computers, right? So a Tesla K80 graphics card has 4,992 cores. Let me say that again. A Tesla K80 graphics card, and it costs a couple of $1,000. It has 4,992 computation cores compared to 8 cores in an i7 Intel processor. So an i7 Intel processor. Now, there are different kinds of cores. The ones in an i7 Intel processor are designed for general computing, and the cores that are designed for artificial intelligence and supercomputing, those are specialized to perform floating point calculations. It's the same graphics cards that they stitch together when they're doing special effects for Jurassic Park, for Star Wars, all the special effects you see in movies, that requires huge quantities of numerical computations. Well, if you take that same idea and then you yoke that for computations, you can really do some amazing things. And that's called, those computation cores in the graphics controllers are called CUDA cores. And the development platform that's used to leverage that is called OpenGL. Okay. This is what you can build your own supercomputer that has the equivalent computing capacity of a Cray supercomputer from 20 years ago. And you can do it with $10,000. So you can take a $10,000 investment with video cards, stitch them together, run OpenGL to take advantage of the CUDA cores, and you have today the ability to calculate what it took a $5 million computer to calculate. You can now do for like $10,000. And I'm not exaggerating. I'm not exaggerating. When you talk about artificially intelligent methods of calculating and predicting, that you have a couple of specific types and methods. I want you to be familiar with those. You are going to perform the Monte Carlo method using simulated data sets, right? So you're going to generate a data sample based on random number generation, and then using those random numbers, you're going to perform calculations to simulate what happens in a market environment with financial trades, right? So I think we'll stop here and we'll pick up SQL and NoSQL stuff on Thursday. I'm going to stay in session here. Does anybody have any questions before we close today? Does anybody have any questions going once?
No, aside from how soon the recording's going to be up.
I'm going to put it up as soon as we finish. Okay.
Okay, then I have no more questions.
All right.